And everyone, so I'm going to go ahead now and solve some questions from chapter 10. This is the chapter on fluids and buoyancy and Archimedes' principle and Bernoulli's principle and Pascal's principle. So a lot of principles, a lot of laws. But basically they all involve pressure, density, and the connection between volume flow and those quantities as well. So actually, this is the wrong one. I'm going to start here, number 3. So we're going to start easy and obviously make them a little more difficult as we go on. So we're going to do 2 of them here. They're level 1 difficulty, so not too bad. So number 3. If you tried to smuggle some gold bricks by filling your backpack, they give you the dimensions here. They want to know what would its mass be. So what they're obviously like referencing here is density and mass and that sort of thing. The main equation we're going to be using is the density, which is given by the Greek letter rho, lowercase rho, looks like a p, equals the mass over the volume. And for, here we're dealing with gold, right? And so we need to look up the density of gold, and I actually don't have that on the top of my head, so I'm going to pull that up right here. Density of gold. And we want to work in kilograms per cubic meter. So let's see what that is really quickly. Density of gold. So we'll say 19, well, this is in grams per cubic centimeter. I guess this is a good idea. We'll leave it in this, 19.32 grams per cubic centimeter. So, and they want the mass, right? So so the mass of our sample, right, is going to be the density of gold, right? Let's call it AU for the moment for gold, times the volume. Now the density, I already forgot it, 19.32. Okay, so there we go. So the density of gold, right, that's 19.32 grams per cubic centimeter. We might as well work in cubic centimeters since we're already in, our volume is going to naturally be in cubic centimeters. Our volume, right, is these 3 numbers multiplied together. So it's going to be 54 times 31 times 22, whatever this result is, and that's going to have units of cubic centimeters. Right, so I'll put that in the calculator real quick. So 54 times 31 times 22, and that is 36,828. So 36,828 cubic centimeters. Okay. So we have now our density and our volumes. We can find our mass, right? So the mass, that's just going to be this. So the 19.32 grams per centimeter cubed times this 36,828 centimeters cubed. And the cubic centimeters, as you can see here, the one in the denominator there, we'll cancel that one out. And so we end up just multiplying these 2 numbers together, right? So it's going to be 19.32 times 36,828. And what we get is, say about 7. Yeah, we can write this in scientific notation. We go to 4 sig figs here, right, because of the multiplication. So that would be on mine, so 1, 2, so 7, 7.11 times 10 to the, let's see, 1, 2, 3, 4, 5, 10 to the 5 grams, right? Or we could write this as kilograms, right? This would be fewer kilograms by a factor of 1,000. So this would be 7.11 times 10 to the 2 kilograms. So either of these would be fine. Okay, or number 11. So here they want you to calculate the total force of the atmosphere acting on a tabletop that measures this. So the goal, right, the idea is that we just basically have we have some rectangular face, right, sort of like this, some rectangular surface. Let's assume that it has no depth, right? So it's just a flat, almost like a piece of paper. I mean, it does have depth. I mean, we don't have to actually assume that. We can kind of just do something like that. Pretty thin, let's say. And we know that the dimensions, right, are going to be a 1.7, right, over here. And we'll call this 2.6 meters. And air is pushing down on this, right? So there's some force, going down, right? But there's atmospheric pressure pointing down. And P atmosphere, right? So we can do this, and we could call it 1 atmosphere, but we want to work in standard units, which is pascals. So we'll go ahead, and this is something you would look up, right? So air pressure at sea level, right? That's basically, we'll assume that we're at sea level. And again, this is pretty standard, but basically it's 101.325 kilopascals, which is going to be 1.013 times 10 to the 5 pascals. So we'll use that one. So 1.013 times 10 to the 5 pascals. So that's basically atmospheric pressure. It's also 1 atmosphere by definition. So the basic relationship between pressure and force and area is this, if you haven't seen it already, is that pressure, which is a vector, is force. Pressure is a scale. Well, it's actually a scalar. Well, we'll leave it like that, I guess. Force over area. Don't worry too much about the vector. It depends. It's actually a vector. Let's not. I'll do that, but don't worry too much about it. About that. So therefore the force, right, is pressure times area, and our area is going to be 1.7 times 2.6, right? So the area, this is a vector as well. The area is going to be 1.7 meters, right, times 2.6 meters. So let's see what we get there. 1.7 times 2.6, and that is going to be 4.42 square meters. And so the force will just be that atmospheric pressure, so that 1.013 times 10 to the 5 pascal times the 4.42 square meters of area. So let's see what we get. 1 times 1.103 times 10 to the 5 pascals. So we get 487,526 newtons. So that's that is the force being exerted on that on there. So okay, that's just the atmospheric pressure, right? Now that's a force, and obviously the tabletop exerts a force back on it. So, but anyway, that's the idea. And they want to know what is the total force acting upward on the underside of the table. And so I think what they're just saying here, I'm not entirely sure. I think they're just trying to stress that it's going to be an equal and opposite force acting up, right? Because the table is not moving. It's not moving up or down at all. So let's move here. A little more interesting. They tell you that an undersea research chamber is spherical with an external diameter of 5.2 meters. And they give you the mass of the chamber when it's occupied as that. It's anchored to the sea bottom by a cable, and they want to know, A, what is the buoyant force on the chamber? And then what's the tension in the cable? So we can just kind of picture it like this, right? So here's like the water or whatever. We're down here. It's fully submerged. And so here is the ground. And here's our cable. And then here's our sphere. Kind of like that, right? And so this thing... if we were, this is obviously it wants to float up, right? So there's a buoyant force that's sort of pulling it up, right? It wants to, float upward. And then there's the weight, obviously, going down, right? mg. And the tension is holding it, is also going to be pointing down, because if you were to, you can think of it like basically if you were to cut the rope, it would go up, right? The buoyant force would take over. So the tension and the weight are trying to keep it from reaching the surface, whereas the buoyant force is trying to move it upward. That's the idea. So for A, right, the buoyant force, right, this is equal to the density of the fluid times the volume that's displaced times G, right? This is really just M. I mean, this is density times volume, which is mass, so it has units of force. And this is the displaced volume, right? And what Archimedes' principle says is that the volume of the displaced liquid or fluid is equal to the volume of the submerged object. And so what we need is the volume of a sphere, right? Because the sphere is fully submerged, so that's the volume of the sphere is precisely the amount of volume of water that's submerged, that's displaced. So the volume of a sphere, this is something, you would probably need to look up. It's 4/3 pi r cubed, if you don't remember it off the top of your head. And we have the diameter is 5.2 of the sphere, so the radius is going to be 2.6 meters. So this is going to be 4/3 pi, and then we have 2.6 meters, this whole thing cubed. And then we'll see what we get here. So 4/3 times pi times 2.6 cubed, and what I get is about 73.6 cubic meters. Okay. The density of water, this is seawater that we're going to be dealing with here, right? So seawater density, I think, is 1,000. It's a little bit different than fresh water, just a little different. So let's just check it out. Seawater density. Yeah, it's 1,029 as opposed to like 1,000. 1,000 is water, right? So it's a little more dense than water. So it's 1,029 kilograms per cubic meter. Kilograms per cubic meter. Okay, cool. And G is 9.8, right? So we're good to go at this point. So the buoyant force, right? That's going to be the density. So 1,029 kilograms per cubic meter times our displaced volume of water, which is equal to the volume of the sphere since it's completely submerged, times 9.8 meters per second squared, acceleration due to gravity. So let's see what we get. 1,029 times 73.6 times 9.8, and that gives us 700, so let's call it about 742,200 approximately. Just getting a little lazy here, so I'm going to just, so 742,200 newtons. That would be the buoyant force there, FB. Okay. So now for part B, right, they want the tension. So we can look at this and just kind of set up, say, well, we're in equilibrium, right? So the sum of the forces in the y direction is 0. The buoyant force points up, right? Tension points down, and the weight points down, and that equals 0. And do we know the mass of this thing? They say it's, 74,400. Okay, so that's good. So we can solve for the tension, right? The tension is just going to end up being the buoyant force, right, minus the weight. And I basically just brought this tension over there. And then so it's the buoyant force minus the weight. And that's what you end up with. So the tension is going to be this number we just found, right? So 742,200 newtons minus the mass, which I said is 74.4. So 74,400 kilograms times 9.8 meters per second squared. So let's see what we get. So 742,200 minus 74,400 times 9.8, and that gives us 13,080 newtons. Okay. So that's how we solve that one. That's the tension. So it's good Archimedes principle and all that kind of good stuff. Okay, so number 52. I actually wrote an equation here already. It's not that interesting. Just force equals pressure times area. We already knew that. So they want to know what's the lift in newtons due to Bernoulli's principle on a wing area of 88 meters squared. And then you have air passing over the top and the bottom surfaces, right? So this is like you have an airplane, basically, right? Fixed wing airplane here. So like this is like the wing, and like this is like the tail. And if you look at the wing, it's differential, right? Air passing over the top at a faster rate. So you have a velocity of air sort of moving like that. Call that V1. And then you have more air going this way. Call this V2. As it sort of moves around the wing, like sort of like that. And Bernoulli's, you can demonstrate using Bernoulli's principle that you're going to have a lift force that goes up, right? This is what underlies air travel. This principle, F lift, like that. So we need to find the pressure difference. The area of the wing is fixed, and what we're going to do here is we're going to assume this is a very thin wing, and I'll sort of show you why we assume a thin wing in a minute. But basically, the delta H between this wing, right? So if I look at like just like the difference between this like delta H is small, right? Very small, negligibly small. So we'll say it's approximately 0 meters. So almost like a paper thin wing. Even if it has a small difference, it won't matter at all. So how do we do this? How do we apply Bernoulli's principle? Well, there's a pressure P1 above the wing, there's a pressure P2 below the wing, and Bernoulli's principle, which looks a lot like energy conservation, looks like this, right? So it's P1 plus rho 1 G Y1 plus 1 half rho V1 squared equals P2 plus rho 2 GY2. And in this case, the rho is air, right? It's one fluid, so I don't even need to do those. It's the same substance, it's just air. Plus 1 half rho V2 squared. And because the y, we're assuming that basically because this delta H is small, right? We're assuming that y1 is basically equal to y2. They're the same, right? If this is like y1 is up here, y2 is down below. So because they're the same, right, we can actually get rid of those, right? They'll just cancel out. And I can rearrange to solve for P2 minus P1. So if I do the algebra here, right, so delta P, my difference in pressure, which I'll call P2 minus P1, if I sort of rearrange this stuff, what I'm going to find is that it's 1 half rho, and then it's going to be V1 squared minus V2 squared, if I sort of just rearrange the Bernoulli principle here. So it's 1 half, and then the density of air. Well, that's something we should look up as well, right? So density of air, right? Not very surprisingly. Basically, it's one. It's pretty close to 1, right? So, I mean, we're going to use 1.225. Obviously, it does vary. This is at sea level, and we'll be, we're not at sea level here, but let's just do sea level. 1.225. You'd be given it if it were something different. So 1.225 is pretty close to 1, though, but that's, we'll use this. And then we have these two velocities, right? 280 is V1, and 150, is it 280? Yeah, 280 minus, so 280 squared minus 150 squared. Sorry, I left the units out. Sorry about that. 0.5 times 1.225 times 280 squared minus 150 squared. And we get equal to 34,239. So the change in pressure, right, the difference in pressure, is 32,000. 239 pascals. And then once I have that, right, I can get the area. The area is 80. Well, they give you the area. It's 88 square meters. So the lift force, right, F lift on the airplane wing is delta P, right, times A, times A. And this is going to be this number, this 32,239 pascal times 88 square meters. So let's see what we get here. So about 3 times, approximately, let's see, 1, 2, 3, 4, 5, 6. 3 times 10 to the 6 newtons is the lift. Okay, we have one more problem here to do. I wrote an equation here too, that's good. So it says a viscometer consists of 2 concentric cylinders, and they give you these 2 cylinders, right? And then a liquid fills the space between them to a depth of this, right? So the idea is you're looking at these 2 cylinders, and they kind of go back like this, right? So there's one cylinder sort of embedded in the other cylinder, I guess. And there's a space between them, right? This is like a hollow space between those 2 cylinders. And they say to a depth of 12 centimeters, right? So let's say that this is the fluid. Let's say that this is like, 12 centimeters. Okay. Well, it would be a little higher than that because these are the, I didn't really draw this to scale. Let me actually just improve it a little bit here. I'm just going to draw it like this, maybe. Okay. So that's like the height. That'll be 12 centimeters. Okay. So we have these two different radii, right? So I'll call one of them R1 and R2. So I'll call this one R1, and then I'll call this one R2. So I exaggerated this, right? It should be a very small space between them, but that's fine. I want you to be able to see what's going on. And they say the outer cylinder is fixed, so this one's not moving, but then the inner cylinder is gonna move at a particular angular velocity, and they want to know what's the velocity, the viscosity of the liquid. So you can see here there's a relationship. This is the viscosity equation. It says that the force is equal to, this is the Greek letter eta, eta, that's basically viscosity, times the area, times a velocity over the length that it's acting over. So, okay. But we're given a torque, right? So we want the viscosity. So first let's solve for eta. So if I sort of go ahead and rearrange stuff here, what we're going to find is that eta is equal to the force times that L, right, that length that it's moving through, over the area times V, the flow speed. Okay, so the area, right, let's kind of work through this. So first of all, we have a torque, not a force, right? So that's first of all kind of important. Torque is force times distance, right? So so the torque right here is going to be RF, right? So the question is what is the R that it's acting over, right? So it's acting here, right? So here it's going to be, let's see here. Sorry, I'm just gonna fix this really quickly. Thank you. Sorry. So here we're going to go ahead and do this calculation. And so let's see. Okay, so the force, we're going to do it this way. Torque is force times distance, right? So we'll do it right out like this, force times distance. But we have a force, so the force is torque over distance. Let's think of it like that, tau over r. And the r is going to be the outer radius, because that's what the torque is being exerted over, right? So, because actually it's going to be the inner radius because the outer one is not moving. So it's going to be the torque over R1. Yeah, we'll do it like that. L is the difference between the radii. So L is R2 minus R1. It's the distance, like that. And then I think we're pretty much good. Oh, with the one exception here. So now we have the V, which is equal to omega R, if you remember from the rotation section. Again, this would be R1 because that's what's spinning. So omega, well, we actually just leave it like that because this is what we have numbers for. So now we're going to plug all these numbers in here, right? So we're going to say, okay, eta is equal to the torque, which is, the force, which is tau over R1, like that, times L, which is the difference between those two radii, like that, over the area. We actually have to calculate the area. The area is going to be for a cylinder, right? And so we'll do that as pi, if you don't remember this, right? It's pi r squared, it's 2 pi r h, or 2 pi r l, like that. And then we're going to go ahead here, and let me just pause